Hi, welcome to this lesson on Euclidean geometry, similarity and congruency. Let's have a look at question 4. We're given that ABCD is a cyclic quadrilateral with BC equals to CD. So I'm going to go ahead and mark that on the diagram. So BC and CD are essentially equal chords in that circle. Then ECF is a tangent to the circle at the point of contact C. ABE and ADF are straight lines. Okay, so all that information that's been given to us is going to be useful because we're going to need to use all that information to answer each question. So if you ever feel like you're getting stuck in the question, go back and look at all the information that's given and ask yourself, have I used this piece of information somewhere in the solution? Okay, the first thing we need to do is prove that the line AC bisects angle EAF. So this angle here. So essentially, the goal here, what we want to prove, is to show that angle A1 equals angle A2. If we can show that, then we know that the line AC bisects the angle EAF. Okay, so let's go ahead and prove this. So the proof will go as follows. Well, those two angles A1 and A2 are directly related to the chords BC and CD because the chord BC subtends to the point A and the chord CD subtends to the point A. Alright, so I can say that angle A1 equals angle A2, and the reasoning for that is BC equals CD, that was given, and therefore equal chords subtend equal angles. Okay, and that would be my proof to show that those two angles are equal. So this angle A1 is equal to that angle A2. Next, we want to show that the line BD is parallel to EF. So we want to show that this line here is parallel to this line here. Okay, so to show two lines are parallel, we recall the fun mnemonic device, right? So the fun mnemonic device tells us that we can show corresponding angles are equal, then the two lines between them are parallel. We can show that co-interior angles sum to 180, they are supplementary, then these two sides are parallel. And we can show that alternate angles are equal, therefore the opposite pairs of sides are parallel. So we need to use one of those to be able to prove that the two lines are parallel. So off first hand, I can see a Z shape here, or an N shape, depending if you turn it around. So if I can show this angle is equal to that angle, for example, then we're done, right? Okay, or if I show that this angle is equal to that angle, then we're done. Okay, so one of the two, because this also makes a Z shape. Okay, so let's see how we can do this. Well, first of all, I've used this BC equals CD in the previous question to subtend equal angles here. Okay, so it might not be that again, but it could be. All right, so I'm going to look at all the other information first before I come back to that. I know that I have a cyclic quadrilateral. That won't really help me because the cyclic quadrilateral, the only real two things we could use right now were the fact that opposite angles are supplementary. And that doesn't really give us any angle to work with that we are interested in to show that two lines are parallel. So I don't necessarily think I would use the cyclic quadrilateral theorems here. Next, we were told that ECF is a tangent to the circle. Now that's helpful because there are two theorems on tangents, and the one that can help us here is the tan-chord theorem because we have a tangent and a chord. So I'm going to look at angle CDB. CDB is this one here. Okay, and I'm going to look at angle CBD, which is this one here. So the first thing I'm going to claim in my proof is that these two angles must be equal. Now, why do I say that? Well, I'm going to say that angle CBD is equal to angle CDB, and that's because BC is equal to CD is given. Okay, so it turns out I did need to use that because these two sides are equal. You have an isosceles triangle, BCD. Therefore, those two angles B and D must be equal. Okay. Next, I have that angle FCD is equal to angle CDB. So let's see. Angle FCD is this one here, and angle CDB is this one here. Now, why do I say those are equal? That is by the tan chord theorem. Tan chord. Okay, so don't forget to always write your reasoning out. Okay, and why is that true? Okay, well, first of all, angle FCD is this angle between the tangent ECF and the chord CD. So the segment that it is in this tiny little segment here. Okay, so the alternate segment is this entire bigger major segment of the circle. And the chord subtends to that alternate segment at here, angle CBD. So I should write that first as equal to angle CBD, but angle CBD is equal to angle CDB because of the isosceles triangle that we noted above. Okay, so what I've proven is that alternate angles are equal. So I can say that the line BD is parallel to the line EF by alternate angles equal. Okay, and the alternate angles that are equal is this angle here, FCD, and then this angle, CDB. Okay, so that is the proof that those two lines are parallel. We used alternate angles are equal and the tan chord theorem, along with noting the isosceles triangle there. Okay, next we want to prove that triangle ADC. So let me bring that triangle out so we can see it. So there's ADC. We want to show that is similar to triangle CBE, which is the smaller one here. Okay, so let's go ahead and see how we can do this. So far, I've used this fact twice in two previous questions. I've used the tangent twice. So I have not used the fact that these are straight lines yet, and I have not used the quadrilateral. So let's see what we can do. Okay, so to show that these two triangles are similar, we either need to show angle, 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 or side, side, sides are in proportion. Okay, because we don't know too many side lengths that are given, okay, other than the fact that CD is equal to BC, we don't know anything else about the sides. So I don't think I'm going to use side, side, side. So this means I need to use angle, angle, angle. And because of the order in which they ask you to prove, we need to show that this angle A is equal to angle C. So this angle here must be equal to this angle here. We need to show that angle D must equal angle B. So this angle here must equal angle B here. And we must show that angle C and angle E are equal. That's the goal. If we can show that those angles are equal in that order, then we've shown by angle, angle, angle that those two triangles are similar. So the first thing I'm going to note is that angle ABC, so here's my proof, angle ABC plus angle ADC is 180 degrees. So where do I get that from? Angle ABC is this one here in the diagram, and angle ADC is this one here in the diagram. So that is by cyclic quad, opposite angles are supplementary. They add up to 180 degrees. Okay, so from this, if I make angle ADC the subject of the equation, I subtract this ABC here, I get 180 degrees minus angle ABC. Okay, so that's going to be important. But if you look at 180 degrees minus ABC, what is that actually saying? Well, if I look at this line ABE, it's a straight line. So this is angle ABE here. So 180 degrees minus that angle is this angle here. Okay, because ABE is a straight line. So this is equal to angle CBE. And that is because ABE is a straight line that was given to us. Okay, so whenever you're given information, it's always important that you reference it, because that is usually what you get stuck on if you can't answer a question. Okay, so far what have we shown? Angle D is equal to angle B in these two triangles. And that's exactly what we wanted to show here. Okay, so that's one angle down. Let's carry on. Next, I can say angle ADC is equal to angle CBE. So angle ADC, right, is equal to angle CBE. That's what we've just shown here. All right. Next, we can say that angle BCE equals angle DAC. Okay, so where does that come from? So angle BCE is this one here, and angle DAC is this one here. All right. So where does that one come from? That is the tan chord theorem. So how does that work? Okay, so first of all, angle ECB, this one here, the dot, that is an angle between the tangent and a chord BC. So subtending in the alternate segment from BC, it subtends to A1. But A1 is equal to A2. That's the very first thing we've proven. So that's where I get this argument from. So the reasoning here is tan chord, right? And the fact that angle A1 equals angle A2. Okay, so what have I shown here? Angle C, the dot here, is equal to angle A, the dot here. And now we're done, because we have two angles that are equal to each other in the triangle. So therefore, the very last angles, so angle BEC, must be equal to angle DCA, and that is by angles in a triangle. They must add up to 180 degrees. So these two angles have to be equal. Okay, hence, what we've shown by angle is that triangle ADC is similar to triangle CBE. Okay, so reasoning, angle. Okay, and lastly, we want to show that DC squared is equal to AD times AB. Okay, so again, whenever you have any question like this in Euclidean geometry where you want to show something squared or some quantity is equal to another quantity, it most likely has to do with proportions with triangles. Okay, so let's go back and see, what did we just prove? We proved this similarity, so that might help us in the question. Okay, so here goes my proof. So we've shown that triangle ADC is similar to triangle CBE. Hence, we can conclude some of the following information. So if I look at this side AD in proportion to DC, the reason why I'm doing that is because there's an AD and a DC in the question. So that kind of guides me on what proportions I should be looking for. All right, so if I do that on the left-hand side, I need to take that exact proportion on the right-hand side, CB and BE. So I can say AD divided by DC. Okay, the reason I do that is because AD is going to be in the numerator here, and if I move DC over, I can get it as a numerator term on the left-hand side. Okay, so by similarity, that must be equal to CB over BE. Okay, the reasoning that those two triangles are similar, so therefore those sides are in proportion. All right, so let's look what we have here so far. It's close to what we want, but not yet. Okay, so what I can do is if I cross multiply both sides by BE and by DC, I'm going to get AD times BE equals AD times, not AD, sorry, let's correct that there, DC times BC, or CB, same thing, all right? Okay, so we've got this side here. That's fine, but we don't have this side here yet. Okay, but note that DC and BC are equal. That was given to us as information. So I can replace this BC with DC. So DC times DC is DC squared. That's equal to AD times BE. And that's exactly what we wanted to prove. All right. So again, whenever you get stuck in any type of question, go back to the information that was given to you and make sure that you've used every bit of information to answer the question. Awesome. I'll see you in the next one.